Okay, so we are going to start in on the next section. Are you doing that because of the Super Bowl commercial? Okay. Okay. And then this next section is on word problems. I was going to skip this section, but then Erica said she loves Half-Life so much. I was like, we need to do at least one thing this year that Erica really enjoys, so it might as well be this. So we've kind of like talked a little bit about word problems, about the uses for this, but we have not done so in much depth, and so that's what this section is all about. Are you ready? Are you ready for this? Okay, so you guys know Half-Life? You know what that means? Not the old video game, the actual Half-Life?
Element to decay.
Yeah, half of the element to decay. Okay? And the fun thing about Half-Life is if you keep cutting something in half and then 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 in half, you never get to zero. Okay? So this is how they do, and we'll talk about this in a little bit, this is how they do carbon dating. Like when they find an old dinosaur bone, they can measure how much of something is in there, and then they know the half-life of that thing, and then they can work backwards and figure out how old that dinosaur bone is, because the amount of whatever that substance is in there will never get to zero. There'll always be at least some of it left. All right? So let's do this. Yeah, I feel like we did an example or two of this already, so that's all right. So bismuth-210 is an isotope that decays about 13% each day. What is the half-life of bismuth-210? How much bismuth do you want to start with? 100. Okay. So what I'm going to do is I'm going to write 100 times this trace is muy importante, so don't miss this. Okay? If it's decaying by 13% each day, that does not mean that I multiply by 0.13, because that's how much is going away. What I want to know is how much is left. So how much is left if 13% is decaying? 87%. So I'm going to go 100 times 0.87 to the x. And since we started out with 100 and we want to figure out what the half-life is, what do I set this equal to? 50, because 50 is half of 100. Okay? So 100 times 0.87 to the x equals 50. This number we just chose out of midair. This number is half of that one. And the 0.87 is because if we lose 13%, that means we keep 87%. All right? And now we just have to use our mad skills solving logarithmic equations to solve from here. What do I do first? Divide by 100. And so when we divide by 100 as our first step, what is 50 divided by 100? 1/2, which I'm going to write as 0.5. So we don't actually have to do that. We could just skip to, can you even read that? We could just skip to the 0.87x, 0.87, to the x equals 0.5 and avoid the beginning part. Because no matter what we choose to start with, if we divide both sides by that, we're always going to end up with half. So how do I solve this? Log both sides or natural log both sides, doesn't matter which one. So if I log this side, the reason that I do that is it allows me to move the exponent to the front. Then how do I solve that for x? Divide by log of 0.87. And divide this side by log of 0.87. So you can do the rest on your calculator. Don't forget to close the parentheses on the 0.5 before you divide by the log of 0.87. And when you do that, what do you get? 4.977286, which is about 5 days. Okay? So the half-life of bismuth 210, sounds like I have a lisp when I say bismuth. Bismuth 210 is about 5 days. Okay? Questions on that? Erica, have you ever done anything easier in your life? I didn't think so. All right, let's try another one. This time it tells us what the half-life of cesium-137 is. It's about 30 years. Was that days or years? Oh, day. Okay, so that decays fast. If we begin with 200 milligrams of cesium-137, how much will there be in 30 years? Close. If the half-life is 30 years and you start with 200, then that means in 30 years there will be half as much left, so you'll have 100. How about in 60 years? Well, that's another 30 years, so that means the amount you have will have cut in half again. How about in 90 years? 25. And you just keep doing that. If you go by 30-year increments here, then you have to cut these in half each time. Nice job there, fella. So notice that what makes this exponential is that these numbers are going up by the same amount each time. This is being multiplied by the same amount each time. So it's not, if they were both going up, then it would be linear. Okay? All right, what else we got? Oh, let's find the annual decay rate. Okay? So this says cesium-137 has a half-life of about 30 years. Find the annual decay rate. So the way that we're going to do that is that it gets cut in half once every 30 years. So instead of raising this to the x power, if I did that, then that would imply that it gets cut in half once every year. I'm going to raise that to the x over 30 power. You see how that happened? Yeah? Okay. So if I want to figure out what the annual decay rate is, then I need to rewrite this so it's just to the x power. So I'm going to use my properties of exponents to rewrite this as 1/2 to the 1/30th to the x, because when you're raising a power to a power, you just multiply the exponents, yeah? So these two things are the same thing. So to figure out what my annual decay rate is, I need to go the 30th root of 1/2, or 1/2 to the 1/30th power. Either way should be same. Thanks for filling in for Cooper and putting your feet up on. Yeah, yeah, got it. No, it's someone's got to do it, and today you're that guy. What is 0.5 to the 1/30th power? Seems wrong. That's what you got too. 0.977. Oh no, that's fine. What does the book say? No, we're good. So you got what now? 0.977. Okay, so that's not the decay rate. That's how much. Nope. Are you doing it with the square root?
Not square root, but like.
So what have you typed in your? Root, right? No, the 30th root. Oh. Okay. Yeah, you can either raise it to the 1/30th power. Yeah, no, you're good. That's fine. It is the right answer. So you can either raise it to the 1/30th power, or you can take the 30th root. But raising it to the taking the 1/30th root would be like raising it to the 30th power. 0.97715. Okay, so that's how much is left after each year. So what's the decay rate? How do I figure out what the decay rate of this is? If this is how much is left, in other words, after each year I still have, 97.715% remaining. Close, not quite. How do I figure out how much is going away if this is what percent's remaining? No? What? Subtract from 100, yes. So if I go 100 minus that, then I'm left with 2 what? 0.285% decay rate. Is that what the book says, Brianna? Well, that's his fault because he rounded to 1.5. Yeah. No, it's fine. So I feel like there's a lot going on in there that's kind of simple, but if you're not on it, then you might miss a few steps. You guys, are you okay with this? Yeah. Do you know where the 1/30th power came from? Because it's 30 years. So that gave us this number right here, which make sure you know how to do that on your calculator. And then that's not the answer to the decay rate. That tells us how much is left. So to figure out what the decay rate is, you could either go 1 minus that, or you could change it to a percent and then go 100 minus that. Okay? Okay. All right. Chemistry. Everybody loves it. All right, let's try a couple more. This says carbon-14 is a radioactive isotope that is present in organic materials and is commonly used for dating historical artifacts like dinosaur bones, pottery shards, things like that. Carbon-14 has a half-life of 5,730 years. That's why it's a nice one to use. It has a really long half-life. If a bone fragment is found that contains 20% of its original carbon-14, how old is the bone? What do you think? What do you think? Huh? Nothing? What am... that means it lost 80%, but we're not ever really worried with how much it lost. We're always worried with how much is remaining. Okay? Anybody have any bright ideas? How much did the bone fragment start with? 100. Kind of. How much does it have left now? 20. And then it loses a half or whatever every 5,730 years. Okay, so there's our equation. Huh? Okay. Right, so divide both sides by 20. So like Brianna said, this is kind of like the very first one we did, that we didn't really have to pick a starting amount because our first step was going to be divide by that, and we were going to end up with 0.2 no matter what. What do you want to do now? Okay, so Dylan's going to tackle this thing. Oh, sorry. Is that a dojo point? Wait, but I think I did that backwards. Hold on, I did that backwards. We're starting with 100 we want, and we only have 20 left. So that's why I'm confused. Apologies. So this is supposed to be a 0.2, but we started with 100, and now we only have 20 left. So I'm sorry, I got that backwards. Okay. Okay. The next thing then that Dylan did is he's going to get this into a single thingy. So he took 0.5 and raised it to the 1 over 5,730th power. And what'd you get? 0.999. Equals, sorry. Got sucked into the 2 there. Okay, so 0.2 equals 0.999879039 to the x. Notice that that's really close to 1 because the half-life is so long. So what do you do now? Log both sides. And then I'm going to take the log of 0.2 and divide it by the log of this. Right? So that would be... the log of 0.2 equals x times the log of I don't want to write all that out, so I'm going to go 0.5 to the 1 over 5,730th power. And if you want to be more accurate and you don't want to get in trouble with Brianna for rounding too early, you should divide by the log of 0.5 to the 1 over 5,730th power instead of writing out that whole decimal. And when you do that, how old is the bone? 13,304. Okay. And that should make sense because if the half-life is 5,730 years, then after 5,730 years, there will be 50% left, right? And then after another 5,730 years, so that's a total of 11,460, there would be 25% left, because that's half of 50%. And then this is a little bit after that, okay? What's the matter, Sydney? Or you just, oh, okay. You weren't asking a question, you were just complaining about life? Okay. All right, we don't have much time, so we should probably stop there, and then you can do some half-life problems, right? Okay. Is there already only 15 minutes left in class? Okay. Not have homework. That